Hi everyone, we have talked about Rankine cycles like crazy up to this point. It is time for AC cycles, which are fun. And I guess Rankine cycles you see a lot of places too, but a lot of like smaller and everyday applications, which I guess cars and power plants and stuff. Anyway, AC cycles are awesome too. And I'm excited to shift from purely Rankine cycles to be able to talking about this AC cycle as well, which these are also called refrigeration cycles in general. Not a big deal either way what you call them, but basically the goal of an AC cycle is to transfer heat from a cold space to a hot space. So you'll notice how that's kind of funky because when we think about delta T being the driver of heat transfer, stuff usually moves from hot to cold. So delta T, heat is going to move from hot to cold. When you open your door on a cold winter day, that heat is moving from the outside to, or from your house to the outside. Because your house is hot, outside is cold, it's letting that heat out. So when your mom said you're letting the cold in, not true, you're letting the hot out. We are going to talk through here, similarly to what we did for a Rankine cycle, is starting with a line diagram. Okay, so line diagram, let's think about here. I want to draw kind of our divide here of thinking about our hot space. And this is our cold space. And let's think about running your air conditioner wherever you live in the summer. And your hot space is around 70 degrees Fahrenheit. And or 90 degrees Fahrenheit. Let's go 90. So it is 90 degrees outside on a hot day. And you're trying to keep your house at 70 degrees Fahrenheit. So we have a delta T here. Our delta T is 90 minus 70. Naturally, hot space, so from outside, the sun is blazing, it's hot outside, it's going to want to move into the cold space. And eventually, your house will heat up from 70 to 75 to 80 to 85 to 90. And you can end up at thermal equilibrium with the outdoor space, which is why we have air conditioners. We don't want that to happen. We don't want to be hot and stuffy in our house. We want to be able to feel cool in the summer. So let's think about the components here. And we are going to have a lovely box up here we're going to start with. And we're going to have a lovely box down here. And let's draw this line a little bit longer here. And we are going to start out our point 1 on a AC cycle. We are going to consider, where'd my blue go? We are going to consider, as we go through this little heat exchanger here. And that heat exchanger is what we are going to call an evaporator, because it is one. So we have an evaporator, and at the inlet of this, we're going to be at about 25 degrees Fahrenheit. So you'll notice that that's pretty cold. But in an evaporator, the goal is to evaporate whatever that fluid is. So our working fluid is coming in here. It's going to be at 25 degrees Fahrenheit. You're on your cold space side, but it is 70 degrees Fahrenheit in your cold space. This is only 25. So you are going to get Q in to this evaporator. And we'll show it on a TS diagram in just a second, But not much temperature changes to this working fluid during the evaporation process because we're going through a phase change. You are evaporating a liquid into a vapor, so the temperature change isn't much. So when we come out of here, we're at 25 degrees Fahrenheit, and we need to now think about, on our hot side, we have to have something hotter than our hot space so that our delta T can move from hot to cold. So what we do there is we have what is called a compressor. Looks kind of like our pump here because it's compressing, but this is a vapor. Pumps don't work well on vapors, so we have a compressor. And coming out of our compressor, when you compress something a lot, go back to the ideal gas law, you increase pressure, your temperature is going to increase. So by here, we are at 120 degrees Fahrenheit, which is hot. So then we're able to go through another heat exchanger here for our working fluid. And because our fluid is at 120 degrees Fahrenheit and our hot space is at 90 degrees Fahrenheit, we're going to have Q come right out of there. Oh, and I forgot here, we have to pay to run our compressor. It's going to take some energy to be able to compress this vapor into a high pressure, high temperature vapor. And you are going to lose a little bit of temperature here. So the temperature is going to change. Let's say it goes down to 110 degrees Fahrenheit. And that is what comes out of what we call our condenser, because the vapor is being condensed down, we'll look at it again on a TS diagram, through this process. But we still haven't quite gotten back to, we're at 110 degrees, we need to get this back to 25 degrees so it can go back through this evaporator and start the process again. And what it goes through here is called an expansion valve. And an expansion valve is just that, it's a valve. It doesn't have any moving parts, there's no heat transfer that happens here. It just puts it through a lot of head loss and releases pressure, which again, opposite of what happened in the compressor. We are able to lower the pressure, which lowers the temperature back down to 25 degrees. And so we are able to use these heat exchangers and these components of compressor and expansion valve to be able to adjust our temperature and pressure so that we can go through the cycle and work opposite to what this feels like, of we're able to take Q from our cold space and eject it to a hot space, which is counterintuitive, but kind of awesome. And that's how our fridge works, that's how our air conditioning unit works, that's how the air conditioning unit in your car works, and we're able to, counter this process by using heat exchangers. So I'm looking at my notes to make sure I didn't miss anything. But I think, you're using this working fluid to store these energies that you're transferring in for a temporary time to then send it out somewhere else. And we use work to be able to do that. And so we are going to go to a TS diagram here. So TS diagram. Okay, TS diagram here. And we are going to start with point 1, which point 1, remember, this is before it goes to the evaporator. And we are going to start at, let's actually draw our constant pressure lines here. And my art skills are not the best here, but that's okay. So we are going to start out at point 1. Is that a different enough color? Probably not. Let me grab another color. Let's try orange. Here's point 1. And this is where it is, oh, I didn't label the numbers over here. Let's go back and do that. So I actually said this wrong. It's coming out of the evaporator at 1. It's coming out of the compressor at 2. Coming out of the condenser at 3, and coming out of the expansion valve at 4. So at 1, we have just come out of the evaporator, and this is at a saturated vapor. And it's a lower temperature saturated vapor, but that's what's crazy about the working fluid. This is definitely not water. This is a refrigerant called refrigerant 134A. There is also refrigerant 22A, but it is banned mostly now because of the potential greenhouse gas implications in atmosphere. Yeah, we're causing problems with 22A. So refrigerant 134A is the common one, but we're a saturated vapor at this point. So this is where we're at on this TS diagram. And if we make the ideal assumption here, but we would go straight up here to be able to draw that, but let's just draw this a little bit angled here, but we're going to be in the superheated vapor because when we go through this compressor, we're obviously very hot at 120 degrees. So that's going to be our point 2 when it comes out of the compressor. And then we go across the condenser. So we're going this direction. Our entropy is increasing, so we're trying to draw this as a real. We'll talk about how to calculate the values and real versus ideal, again, just like we did with Rankine. But across the condenser, you're going to be moving this way to bring it to a saturated liquid. And so here we were a superheated vapor. You're going to go to a saturated liquid at 0.3. Again, let's assume that this is a real cycle, so we're going to be a little bit angled here. We're not going straight down, but this brings us to 0.4, which is again at our lower temperature of 25 degrees Fahrenheit, so that we can go this direction back to 0.1 through the evaporator and go through the process again. So our friction increased the entropy here, especially in our expansion valve. Lots of friction, lots of head loss happening there to be able to make that release happen, kind of like flash release of the pressure. And you can look in your steam tables at how low these temperatures truly are for boiling. So here we are boiling this refrigerant 134A at 25 degrees Fahrenheit. And then we bring it up to 120 degrees Fahrenheit at the superheated stage. And then we're at 110 degrees Fahrenheit at the outlet of the condenser. So after we've just condensed, this is a lot higher. But again, think about this is a lot higher pressure as well. So think about the implications of the boiling point and the temperature and pressure relationship there. And then think about what we had as the hot space is 90 degrees and the cold place is 70 degrees. So you're kind of using these different directions of where the evaporator is here, the compressor is here, the condenser is here, and the expansion valve is here. So you're able to go through this process and take Q and turn it into Q on the hot space side. And then again, this takes work on the system to be able to make that happen. And the reason why we don't have anything on this side for expansion valve, again, is because an expansion valve doesn't have any moving parts. And in order to create work, you've got to have a force on a distance. If nothing is moving or applying anything to this fluid, we're not going to have work. And even though the temperature is changing pretty drastically here, this is a flash process just releasing the pressure, and we can insulate these expansion valves so basically Q isn't happening. Again, this is a good look it up, explore, and look at expansion valves. Very interesting. Not going to talk about all the details in this class. But that's the overall process of the AC cycle. We'll come back for part 2 to talk about the different points and how it compares to finding the different points for enthalpy which is turning into power and efficiency for a Rankine cycle, translating that to an AC cycle. So see you soon for that.